Hi, my name is Manikanta, and in this video I am going to explain about atomic layer deposition, which is also known as ALD. ALD is a true nanotechnology allowing ultra-thin films of a few nanometers to be deposited in a precisely controlled way down to the atomic scale. ALD holds tremendous promise across wide arrays of industries including energy, optical, electronics, etc. There are basically two defining characteristics of atomic layer deposition. They are self-limiting atomic layer by layer growth and highly conformal coating. Generally, conformal coating materials are applied to electronic circuitry to act as protection against moisture, dust, chemicals. And for this protection to act properly, it has to cover the whole surface. And ALD systems can be designed to deposit pinhole-free coatings that are perfectly uniform in thickness, even deep inside pores, trenches, and cavities. In atomized spray coating, the films produced are usually quite thin, and it provides the required thickness of the conformal coating. And the process of layer building also improves edge coverage, since the subsequent layers have a greater affinity for the previously applied layer. ALD uses chemicals called precursors. Precursor is nothing but one of the compounds that participates in the chemical reaction. ALD uses precursors and alternating surface reactions to grow self-limiting layers of film. By repeating the process of growing individual layers, thin films can be applied to surfaces. And some advantages of self-limiting film include uniform surfaces, high conformity, high control and accuracy of atomic level thickness, and etc. ALD does have some limitations including slow rate of reaction, etc. Research is still being conducted to more completely understand the process of ALD and how to improve it. ALD is similar to other common deposition techniques such as chemical vapor deposition and molecular beam epitaxy. It contains two reactants A and B which react to form a product or products. When a solid surface is exposed to a gas phase, the gas molecules absorb to the surface due to the various intermolecular forces that attract the molecules to the surface. In ALD, enough time must be allowed in each reaction so that a full absorption density can be achieved. One of the fundamental differences between ALD and other deposition techniques is that the way in which the reactants are exposed to the substrate. In ALD, the reactants A and B are individually exposed to the surface, allowing for sequential layering process to occur. What is meant by self-limiting is that once a complete monolayer of reactant molecules bonds to the surface molecules, then the bonding of any other reactant molecules to the reactant molecules that constitute the surface monolayer is unlikely to occur, and one ends up with just one layer of the reactant molecular species. There are two aspects of absorption that are essential to the understanding of ALD. First, the bond strength that binds the gaseous species to the surface varies depending on both the gaseous species and the nature of the surface. Secondly, the rate at which absorption occurs will be finite and in some cases may be quite slow. In general, any solid surface exposed to a gas or vapor will retain at least some of the gas or vapor on the surface after all gas phase molecules are removed. The forces holding the molecular species on the surface can be weak or they can be quite strong. In the latter case, in particular, the absorbed molecules tend to readily form the self-limiting monolayers of interest for ALD, and such layers can be fairly stable at moderate temperatures. A physisorbed monolayer, on the other hand, may be readily desorbed if the substrate surface runs too hot because of the weak bonding forces. Once a monolayer of a first reactant is formed, then the introduction of a second reactant simply converts the first reactant to a layer of some desired solid material. All gases will physiabsorb a self-limiting monolayer under the correct temperature and pressure conditions, even if they do not chemisorb. The preferred conditions are low pressure and moderate temperatures. In ALD, neither temperature nor flow uniformity are of great importance in determining the quality of the films formed. As long as the temperature lies within the temperature window, the uniformity of the local temperature on the substrate surface should not influence film characteristics. Similarly, the local concentration of reactant molecules does not need to be uniform, provided that all parts of the surface receive at least enough molecular flows to form a monolayer of the reactant. For the above said reasons, it is not difficult to deposit very uniform films over large area substrates by the ALD process. At the same time, because the films are deposited a layer at a time, they tend to be very conformal over uneven topography also. As a final point, it is possible by ALD to grow multi-layer thin films known as nanolaminates. That is, we can tailor the film characteristics by depositing alternate layers of different materials sequentially. In other words, one can deposit designer films as with this table contains the non-exhaustive list of typical thin films which can be deposited by ALD, and this one is typical precursor compounds that can be used as metal sources in ALD processes. We can see that there are a very wide range of precursors that we can be used. Now I'm going to explain one of the process used to deposit oxide films over substrate. Metal oxides are difficult to deposit by thermal chemical vapor deposition techniques at moderate temperatures. Since ALD methods allow the separation of each reactant until they react at the substrate surface, more highly reactive species may be used and low process temperatures are also possible. Depending on the surface energy of the substrate or the already grown film, the film continues to grow as amorphous or silicon. The films can be amorphous polycrystalline or single crystal depending on the deposition temperature also. In general, less than one monolayer of oxide can be formed. Let us see the formation of aluminum oxide over the substrate. The one of the reactants which we use is trimethyl aluminum. In general, less than one monolayer of aluminum is formed at each ALD cycle. A simple explanation for this phenomenon can be offered based on the steric effect. That is, the TMA molecule is quite large and it is therefore not possible to position enough aluminum atoms on the surface in a single monolayer of TMA to yield a full monolayer of aluminum oxide for each cycle. We can only grow at most 0.2 monolayers of Al2O3 per cycle. Anyhow, the first reactant would be the trimethyl aluminum, and the second reactant can be either H2O or oxygen or O3, or we can use many compounds. First we chemisorb the substrate with TMA and then we purge the remaining TMA after the enough TMA getting absorbed on the surface, and then we pass on O2 plasma over the monolayer which got formed on the substrate, and then we purge away the remaining O2 plasma, and the two reactants get reacted and aluminum get formed on the top of the substrate. Only step 3 varies between whether we use H2O or O2 or O3, depending on the process which we use, because there are several types of processes for ALD. The major limitation of the ALD is slowness. We can build only up to 1 to 5 nanometers per minute typically, which can be improved by shortening the cycle time through reactor design. In research reactors typically take 1 to 3 seconds for each cycle, or 0.1 seconds reported for single wafer reactors. And we can also compensate the time by using large batch processing. For example, 82 substrates in display production at planar systems. And what the self-limiting film growth doesn't necessarily ensure is full monolayer by monolayer growth, because it has a steric hindrance where there is only limited number of reactive sites, and temperature independent growth rate is also not necessarily ensured, because there are temperature dependent saturation densities, and atomically smooth films are also not guaranteed, because nucleation can happen, especially in case of polycrystalline films, and absolutely constant growth rate from the very first cycles also cannot be expected, because of the density of the reactive sites on the underlying surface, and film surface itself can be different. But then a lot of research is going on in ALD, and it is a very promising technology. And when we come to the present applications, the main thing, or the basic thing, can be the magnetic recording heads. The magnetic heads which are used in the solid drives, which are used to read and write data into the hard disk. ALD aluminum oxide has been used in gap layers since 2000. Thin conformal insulating film is needed, and ALD saved the life of the whole technology. And we can here see the silicon technology reaching nanoscale, where the gate length has reduced so much by nearly 0.7 times every 2 years because of this nanotechnology. And ALD is also used in creating protective coatings, and in Kalevala jewelry they coat their silver products with ALD alumina. Coatings of coins are also made, and obviously ALD sealing is used industrially in other areas, but not reported in many literatures. And when we come to optics, high uniformity and accurate thickness control make it attractive for optics. And recently, Planar company developed a multiple cavity fabric parrot filter for their WDM applications, and the device consists of about 200 layers and still has a thickness of just 45 microns. It has ALD has even microelectronic applications in depositing gate oxides, the deposition of the high K oxides like aluminum oxide, zirconium oxide, and many other. In DRAM capacitors also we can see the use of ALD, yet another application of ALD, and mainly in biomedical applications also we can see the use of ALD. Nanoporous materials are emerging throughout the biomedical industry in drug delivery, implants, and tissue engineering. The benefit of using ALD to modify the surfaces of nanoporous materials is that, unlike many other methods, the saturation and self-limiting nature of the reactors means that even deeply embedded surfaces and interfaces are coated with a uniform film. Nanoporous surfaces can have their pore size reduced further in the ALD process, because conformal coating will completely coat the insides of the pores. This reduction in pore size may be advantageous in